Hello everyone. In this video, we will talk about the Poisson distribution. The Poisson distribution is used to model the number of times an event occurs in a fixed interval of time or space. The Poisson probability distribution gives the probability of the number of events occurring in a fixed interval of time or space with a known average rate. And the occurrence of events are independent. The occurrences of events are always considered with respect to an interval. The interval may be a time interval, a space interval, or a volume interval. For example, we can use the Poisson distribution to model the number of customers arriving at the bank from 9 a.m. to 10 a.m. Here, the time interval is the 1 hour period from 9 a.m. to 10 a.m. We can model the number of tornadoes observed in a region over a 1-year period. The interval is the 1-year period. We can model the number of typographical errors per page, the number of flaws per unit length of a wire, or the number of organisms per unit volume of some fluid. Let's take a look at the notation of a Poisson distribution. The random variable x follows the Poisson distribution. Here, the symbol is PO with parameter lambda. The PMF of the Poisson distribution is given as P of x equals e to the power minus lambda times lambda raised to the power x over x factorial. X is the number of events occurring. So x can take on values 0, 1, 2, up to infinity. And what is lambda? What is e? Lambda is the parameter, corresponds to the average number of occurrences in the given interval. And e is the Euler's number, the base of the lateral log system, approximately equals 2.71828. And x is the number of events occurring. The mean of the Poisson distribution equals lambda. And the variance of the Poisson distribution also equals lambda. So this is the summary of the Poisson distribution we need in the video. Let's take a look at the graph of the Poisson PMF for different values of lambda. Say lambda equals 4. And here you can see that the graph of the PMF is skewed to the right. And as the value of lambda increases, say lambda equals 8 or lambda equals 16, the graph of the PMF is getting more and more symmetrical. Let's get back to the PMF of the Poisson distribution. If we sum up all the probability from x equals 0, 1, 2, up to infinity, we should get the value 1. So let's verify this. All right, the summation from x equals 0 to infinity of the Poisson PMF, the first term in the numerator, e to the power minus lambda, is independent of x, so we can factor that out. And then we get the expression, the summation from x equals 0 to infinity of the expression lambda raised to the power x over x factorial. You can recall the Maclaurin series of the function e to the power x. E to the power x equals 1 plus x squared over 2 factorial plus x to the power 3 over 3 factorial, etc. Written in the compact form, we get this summation expression, x to the power k over k factorial. And you can see the similarity between these two summation expressions. So here we have lambda raised to the power x. For the Maclaurin series, here we have x to the power k. And then we have x factorial in the denominator. For that part, k factorial. So the summation of the expression lambda raised to the power x over x factorial is simply the Maclaurin series for e to the power lambda. And multiply this with e to the power minus lambda, you get 1. So we verify that the sum of the Poisson PMF from x equals 0 to infinity is 1. Let's take a look at a few examples regarding computing Poisson probabilities. Suppose that the number of typographical errors on a book follows a Poisson distribution with mean 1. A page of the book is randomly selected. What is the probability that there are 3 errors on that page? First, define the random variable. Let x be the number of errors on the page. And we need to identify lambda. A Poisson distribution with mean 1. So here we have lambda equals 1. So x follows a Poisson distribution with parameter 1. We want to get the probability that there are 3 errors on the page. So we want P of x equals 3. Get the Poisson PMF. Substitute lambda equals 1. And here x equals 3. We get this expression, e to the power minus 1 times 1 to the power 3 over 3 factorial. Upon calculation, we get 0.0613. Let's take a look at another example. Based upon previous record, the number of accidents at a particular traffic intersection has a Poisson distribution with mean 2.6 per day. What is the probability that there is at most 1 accident on a given day at this traffic intersection? Define the variable. Let x be the number of accidents on a given day. And then what is lambda? A Poisson distribution with mean 2.6 per day. So lambda equals 2.6. So x follows a Poisson distribution with parameter 2.6. We want to get the probability that there is at most 1 accident. So either there is no accident or exactly 1 accident. So the corresponding probability statement is P of x less than or equals 1, which is equals to P of 0 plus P of 1. Substitute lambda equals 2.6 into the Poisson PMF, and then calculate for x equals 0 and x equals 1 respectively. We get the expression by substituting x equals 0 in the first term and x equals 1 in the second term. Upon calculation, we get the answer 0.2674. How about the mean and the standard deviation of the number of accidents on a given day at this traffic intersection? We have the same random variable x corresponds to the number of accidents on a given day. Lambda is 2.6. And then the mean and the variance equal lambda for Poisson distribution. So we have the mean is 2.6. The standard deviation is the square root of the variance. The variance is 2.6 as well. So the standard deviation is the square root of 2.6, which is 1.6125. So here, the number of accidents on a given day at the traffic intersection has a mean 2.6 and standard deviation 1.6125. Let's take a look at another example. Suppose the number of customers arriving at a clothing store follows a Poisson distribution. On average, there are 42 arriving customers per hour. What is the probability that exactly 50 arrivals in the next hour? In this example, we will use the Excel function. The Excel function for computing Poisson probability is Poisson.dist. It takes 3 parameters. X is the number of events occurring. The second parameter, lambda, is the mean. And the logical parameter, cumulative, true or false. Cumulative equals true when we want to get the cumulative probability, or else cumulative equals false. In this example, we want to get the probability that exactly 50 arrivals in the next hour. First, identify the random variable. Let X be the number of arrivals in the next hour. Lambda is 42. On average, there are 42 customers arriving. So X follows a Poisson distribution with parameter 42. We want to get the probability that X equals 50, exactly 50 arrivals. Plug into the Excel function. We want X equals 50. So the first value is 50. And then the second parameter is lambda. Lambda equals 42. And then the third parameter is false. We want to get the exact value for the PMF at X equals 50. And we get the answer 0.02748. So this is the probability that exactly 50 arrivals in the next hour. Let's compute another probability. Suppose we want to get the probability that fewer than 40 arrivals in the next hour. Use the Excel function again. The random variable X corresponds to the number of arrivals in the next hour with lambda equals 42. We want to get the probability that fewer than 40. So we have P of X less than 40. This expression equals the probability of X less than or equals 39. Because X is a discrete random variable, X less than 40, that means X takes value from 0, 1, 2, up to 39. And we want cumulative probability. So here, the cumulative parameter, we will set it equals true. And we get X equals 39, lambda 42, cumulative parameters is true. And the answer is 0.3581. So that is 35.81% of the time we have fewer than 40 arrivals in the next hour. That's it for today's video. Thank you for watching. In the next video, we will derive the mean and the variance expression of the Poisson distribution.